So, last class we discussed about simple Rankine cycle. That's not again I will explain. So, Carnot cycle, isothermal heat addition. Then there is a limitation in the boiler of maximum temperature 350. Cycle efficiency we can't enhance beyond that limit. Second limitation in turbine blades, two-phase expansion and compression blades, two-phase compression is taking place. To overcome that, the Rankine cycle is proposed. Rankine is proposed new cycle. Their heat addition at constant pressure process. So we are adding heat at a constant pressure process. There is no limitation of temperature. So we can rise more than 350. And second one, we can expand the steam at turbine at single phase expansion. So there is no impeachment of turbine blades, and the compression not by the compressor, by the pump, just rising of the pressure from condenser pressure to the boiler pressure. By using liquid pump, we can compress the liquid. So the energy requirements is a negligible amount of the energy requirements is coming to the picture. So is one more advantage. So we modified the simple Carnot cycle by the simple Rankine cycle. In the Rankine cycle, pump is working and raising the pressure from condenser pressure to boiler pressure by using small pump. Then that liquid is entering into the boiler, adding sensible heat, then latent heat, next sensible heat to the boiler, and superheated steam coming from the turbine outlet. It's a boiler outlet and it is entering into turbine, it is expanding in turbine up to condenser pressure. The outlet is dry stream, not wet stream. Dry stream or dryness fraction may be more than 0.95, 0.8 like that. That is allowable range. Then that steam is expanding in the condenser. This is a simple ideal reversible cycle. But coming to the practicality, this is simple ideal reversible cycle. But coming to the practicality, constant pressure heat addition is possible or isoentropic expansion is possible. If it is not possible, we have to consider that losses. Then we will get the actual simple Rankine cycle efficiency. So at constant pressure heat addition, we are assuming practically it is possible. Some pressure drop will occur. Why? Because shell and tube heat exchangers we are using. Due to pressure drop, some heat drop also, temperature drop also will occur. Like a specific volume is fixed. The next turbine, isoentropic expansion. Isoentropic expansion means there is no heat loss. Whatever the internal energy of the steam is there, that totally expanded and work converted as a work. But in practical case, if any person visited turbines, turbine surrounding the turbine shell contains one water jacket where the heat suction is observed, means we are providing cooling facility to the turbine. Means some heat loss will occur in turbine. That's the meaning. Otherwise, there is no heat loss from the turbine. So we have to consider that turbine heat loss also. And condenser also we are using constant pressure heat rejection. But coming to the actual cycle, in the condenser pressure also constant pressure heat addition. There also same thing, shell and tube only. How it is practically possible? Some pressure drop will occur, temperature drop will occur. So pump also like that only. But pump we can neglect because specific one is very low. The work input itself negligible. Then actual or real condition also variation is the quantity wise. Percentage wise variation is there, but quantity wise variation is less. So up to BTech level, we are considering high grade energy inputs or energy outputs, the high grade energy interactions, whatever the work loss is taking place, that loss we are considering for actual cycle. For low grade energy interactions for BTech level, we are not considering. We have to consider that is a reasonable amount only loss is taking place in actual cycle. But coming to the practicality, the high grade energy is very important. So we are considering high grade energy deviation. You see, this is the actual curve. Some pressure variation is there and some isoentropic process deviation is there. Next, some pressure variation in the pressure drop in the condenser is there. and some isoentropic deviation in the turbine also, the pump also is there. But in practical case, what we are considering? We are considering only the pump losses and turbine losses for calculation of the actual efficiency of the vapor power cycle. Isoentropic efficiency of turbines we are considering. What is the isoentropic efficiency of the turbine means? Actual turbine work output by isoentropic turbine work output. This is the actual turbine work output. But by the calculation isoentropic efficiency we are assuming by Euler diagram we are extracting H3 and H4s, and difference of the enthalpy is the turbine output. But this is the isoentropic process. But actual process work output we want to calculate. Actual always less than, output always less than the theoretical. So actual work output by isoentropic work output of the turbine is called isoentropy efficiency of turbine. Generally, but high capacity turbines, isoentropy efficiency turbine 90 to 95. For supercritical means 95 you can consider. The deviation of the pressures, enthalpy deviations are less, 95 for high pressure. For medium pressure, low pressure, 85 to 95 it is varying. Isoentropic efficiency of turbine. So the first isoentropic turbine work output first we are calculating based on the pressure and temperature operation. In the problem they will give the deviation of the turbine efficiency, isoentropic efficiency. By using that one, actual turbine work output we are calculating. Second, I already mentioned high grade energy interactions only we are considering for actual cycle, real cycle. Isoentropic efficiency of compressor or pump. Second one, isoentropic efficiency of compressor or pump. It is the defined as ratio of inputs. In the input point of view, actual input is high compared to isoentropic input. Same figure. This is the actual input, the isoentropic input. This is the deviated actual input. You see, actual input is higher than the isoentropic input of the pump or compressor. Why? Because in Carnot cycle we are assuming it is a compressor. If Rankine cycle we are assuming it is a pump. So isoentropic pump work input divided by actual pump work input is called isoentropic efficiency of pump. The isoentropic efficiency of pump low capacity 75 to 85. Maximum that range is 75 to 85. Low capacity is 75, high capacity 85. Even the efficiency is less, the value magnitude is less. Why? Because the requirement itself is very less compared to output. That's why magnitude is less. Percentage point of view, isoentropic efficiencies are low for pumps or compressors. Okay, the isoentropic efficiency of pumps work input divided by the actual pump work input. So these two high grade energy interactions we are considering for determination of the actual real cycle, Rankine cycle efficiency. So same problem, what are the problem we discussed? Same problem we will solve. Just we considered the isoentropic efficiency of pump and isoentropic efficiency of turbine. See the problem first. Anytime first read the problem. Based on the given data, you extract the properties from the steam table or from the Euler diagram, whatever, and mark the points and calculate the thermal efficiency of the Rankine cycle. The first, consider a steam power plant operating on the simple ideal Rankine cycle. Consider a steam power plant operating on the simple ideal Rankine cycle. Steam enters the turbine at 3 megapascal. The steam enters the turbine at 3 megapascal and 350 degrees centigrade and is condensed in the condenser at a pressure of 75 kilopascal and is condensed in the condenser at a pressure of 75 kilopascal. Same data, 30 bar pressure and 0.75 bar. 30 bar present, 350 degrees centigrade. 0.75 bar, what is the temperature, or means by isoentropic expansion you can extract the temperature also. Determine the thermal efficiency of the cycle first. If the isoentropic efficiency of turbine is 87%, the isoentropic efficiency of turbine is 87%, and the isoentropic efficiency of the pump is 85%. The isoentropic efficiency of turbine is 87%, and the isoentropic efficiency of pump is 85%. Determine the thermal efficiency of the cycle and net work output of the plant for the mass flow rate of 15 kg per second. Up to now, net work output kilojoules per kg we are determining, but here they are asking net work output at particular mass flow rate, means kilojoules per second into kilojoules per kg into mass flow rate, kg per second, kg cancel, kilojoules per second we will get, or kilowatt, the work output. Okay, simple problem. At 30 bar pressure, what is the HF value, saturation liquid, and saturation gas value, and entropy of the saturation gas, T saturation temperature and T superheated temperature. Specific heat we assume 2.1. At 0.75 bar, again HF value, SF value, VF value, SG value, and T saturation temperature. Okay, same whatever the two problems already solved. Determine the H1 value. H1, extract the H1 value at 0.75 bar saturation liquid, 384.43. Next, pump work input in isoentropy process we are assuming. So Vf into P2 minus P1, then we get 3.3 kilojoules per kg. But here they give an efficiency of the pump. Isoentropic pump work input by actual pump work input. The isoentropic efficiency is 85%, then actual pump work input is isoentropic pump work input divided by efficiency of pump, we will get 3.88 kilojoules per kg. Here we determined the actual pump work input. First isoentropic process, what is the work input we calculated, and divided by the isoentropic process efficiency, we got 3.88 kilojoules per kg. Okay. Then H2 equal to enthalpy, the pump outlet enthalpy equal to inlet enthalpy plus pump work input. That's all. Work input is actual work input, 384.43 plus 3.88, 388.31 kilojoules per kg. Next, H3 means H superheat, boiler outlet, Hg plus Cp into T superheat minus T saturation. Then you will get the Hg value. Then boiler, H3 minus H2, we will get boiler heat input is 2658.8. Then determine the S superheat value. The S superheat Sg plus Cp into Ln T superheat by T saturation. Then turbine inlet and entropy and turbine outlet entropy is same. Isoentropic process, S3 equal to S4 equal to Sn, Sx equal to Sf plus X into Sg minus Sf. Then X we determine 0.864. The X value is 0.864. By isoentropic process we are assuming, we are determining superheated entropy. Same entropy is there, and 0.75 bar SFSG we substituted. Then we determine the X value. Once we know the dryness fraction, then the turbine outlet enthalpy we can determine the H4 at dryness fraction 0.864. Then turbine outlet enthalpy is 2353.27 kilojoules per kg. Then isoentropic turbine output equal to H3 minus H4. Then you got 693.86 kilos. But some heat loss is taking place, so that much of output you will not get. The given turbine isoentropic efficiency of turbine is 87%. Isoentropic efficiency of turbine is equal to actual turbine work output by isoentropic turbine work output. Then turbine actual work output equal to efficiency of turbine into Isoentropic turbine work output. We got actual turbine work output 603.66 kilojoules per kg. In isoentropic process 693.86. How much reduction is there, you see? 603.66. Then determine the efficiency. Network output by heat input. Network output. Actual turbine output minus actual pump input. 603.66 minus 3.88. We got 599.78 kilojoules per kg. Then efficiency of thermal efficiency of plant. Network output by heat input. We got 22.55. For ideal cycle 25%. For Carnot cycle 42%. You can cross verify. In actual simple Rankine cycle at 30 bar I am running, we got only 22%. If ideal cycle I am running 25%. If I Carnot cycle if I run 42%. Next. The net power output of the plant at mass flow rate of 15 kg per second. The net power output equal to mass flow rate into net work output per kg of steam. The mass flow rate is 15 kg per second. Multiply. You got 8,996.7 kilojoules per second. So simple problem. Only one example I am giving, and also properties myself I already extracted. So for solving problem it will take more time. First extract the problem and draw the TS diagram or schematic diagram, mark the known points, then by using Euler diagram or steam table you can calculate the work input to the pump, heat input to the boiler, turbine work output and condenser heat rejection. If isoentropic efficiencies they are providing, then determine the isoentropic work input to the pump or isoentropic work output from the turbine. Then you calculate the real efficiency of real thermal efficiency of the Rankine cycle. Okay, with this we are concluding today's lecture. Tomorrow we will discuss how we can enhance the efficiency of Rankine cycle. What are the methods available for enhancement of efficiency of Rankine cycle? Okay.